Hello everyone, myself Dr. Divya, Assistant Professor at Department of Chemistry, Institute of Aeronautical Engineering, Hyderabad. So today we will discuss about the electrochemistry, which will able to understand the reference electrodes and its uses, then electrochemical series, its application, Nernst equation and its application. So here are the topics: reference electrodes, then standard hydrogen electrode, then what is secondary reference electrode and its construction like calomel electrode, then what is electrochemical series and its applications, and Nernst equation and its applications. So what are reference electrodes? These are the electrodes which will help us in finding out the electrode potential when coupling with an unknown electrode whose potential to be determined. So the primary reference electrode is nothing but it has an electrode potential which is fixed to zero, So the important primary reference electrode is standard hydrogen electrode. Standard hydrogen electrode, which is abbreviated as SHE. So what does a standard hydrogen electrode consist of? It consists of a platinum wire. Here we can see the platinum wire inside the inverted glass tube. Then hydrogen gas that is passed through this glass tube at 1 atmospheric pressure, which is standard condition. Then a platinum foil attached end of this wire. This is the platinum foil. Then this electrode is dipped in 1 molar H plus ions at 25 degrees centigrade. 1 molar. This solution is 1 molar H plus ions like acid. So the potential of this electrode is 0 at all temperatures. The potential is always 0, which is fixed. So this will help in finding the potential of other electrode. So let us see the reaction that is taking place at a standard hydrogen electrode. So the platinum dipped in H plus ions, the hydrogen ions gas is passed. So if the potential of coupled electrode, when this electrode is coupled with other electrode or unknown electrode potential. So that will give so when it is coupled with unknown one, so it is unknown. So what happens if it is greater than 0? If the electrode potential of unknown is greater than 0, then the standard hydrogen electrode will act as anode. So oxidation takes place. So H2 gas that is passing through this electrode will convert to 2 H plus ions and liberates 2, and 2 electrons are given out. And what happens if the unknown electrode potential is less than 0, then standard hydrogen electrode will act as cathode. So this cathode will take up. So this SHE will take up. So the ions, the H plus ions present in the solution will take up 2 electrons and give hydrogen gas. This will bubble in the electrode. So based on these electrode potentials of any metal, so based on these reactions, the potentials of the metals can be calculated, and based on the potentials with reference to hydrogen, electrochemical series is obtained. So there are some limitations. So this is used for electrochemical series, but there are some limitations for standard hydrogen electrode due to its difficulty to construct. Why? Because hydrogen gas to be maintained at 1 atmospheric pressure, and a platinum plate to be used, or the mesh to be used, which is expensive. Then the activity of H plus ions to be maintained at unity, which is also a difficult task. Then the platinum metal has high absorption and catalytic property. So this catalytic property will or the absorption property will cause some disturbances, like hydrogen on platinum surface is reduction catalyst, so it will get reduced. So and also the number of organic substances get reduces, and inorganic ions like iron Fe+3 and manganese oxide get reduced to their lower valence state. The cations that are like silver, copper, cadmium, lead will get reduced and get deposited on the platinum metal. Platinum metal. Platinum metal. So like this, there is some interferences taking place with the electrode. So due to this, there is again a need for a next electrode or the secondary reference electrode. So because there is a difficulty in maintaining H plus ions in the concentration of H plus ions in the standard hydrogen electrode, and also the pressure of the gas to be maintained. So also and one more thing is the poisoning of the electrode due to trace impurities in the gas. Gas should be high pure, otherwise there is poisoning of the electrode. So that is why there is a thought again like a secondary reference electrode to be used in place of SHE, alternative to SHE or standard hydrogen electrode. So it is nothing but example calomel electrode. See, this is the physical appearance. This is the physical appearance of calomel electrode. This is how a calomel electrode looks like. This is how the calomel electrode looks like. So we will see the schematic how the calomel electrode is constructed and is used for electrode potential determination. So the main reaction that takes place in the calomel electrode is the reaction between metallic mercury, elemental mercury, and the mercury chloride, and the aqueous solution that is present in the electrode, that is nothing but KCl present in contact with the mercury chloride and mercury paste. That is the reactions that will take place, that we will see in detail in the next slides. It consists of a glass tube. So this is the construction. It has a glass tube made up of glass and contains mercury at bottom. This is the mercury at bottom, and covered with a solid mercury chloride, solid mercury chloride and mercury and a mercury paste. So this tube is again filled with KCl. Potassium chloride solution, and the platinum wire is in contact with mercury, acts as an electric contact. So the platinum wire, this is the platinum wire which is in contact with the mercury and acts as electrical contact. Okay, so this is the cell notation of the electrode. Chloride minus ion to separated. This is a separation between the solid and liquid. Then mercury chloride in the solid form. Then mercury in liquid form, because mercury is a liquid at room temperature. Then platinum, which is the wire that is connected. So here are the reactions that will take place in the calomel electrode during its usage. So the reduction reactions takes place where mercury chloride takes up electrons and forms mercury and chloride ions. So the potential of this electrode is given as E calomel is equal to E naught calomel, or the standard E naught of calomel, then minus 2.303 RT by 2F log chloride ions, concentration of chloride ions. So as we see from the formula, the whole story of usage of calomel electrode depends on chloride ions, usage of calomel electrode depends on chloride ions. So it is again written as E naught Calomel is equal to 2.303 RT by F log concentration of chloride ions. So this chloride ions, presence of chloride ions is very important. The concentrations of chloride ions is also very important for a calomel electrode. So when it is 0.1 molar, 0.1 molar KCl is used, the potential will change because it all depends on the concentration of chloride ions. So 0.33 volt. When the concentration is 1 molar, it is plus 0.28 volt. When it is saturated, then it is plus 0.24. What is saturated? KCl is added to the water until no KCl can be dissolved. No KCl can be dissolved. That is called saturated. It reaches a saturation point. Saturation point of dissolution. Saturation point. So that forms a saturated KCl solution. So what is the main important thing? The use of calomel is it is convenient to handle and easily can be constructed. It is convenient in handling and construction, but it cannot be used beyond 50 degrees centigrade because mercury is unstable at 50 degrees centigrade or beyond 50 degrees centigrade and becomes poisonous. Neurological effects takes place. So it should not be used beyond 50 degrees centigrade of temperature for any cell. So then electrochemical series. So depending on after calculating the electrode potentials, they are arranged in a series from highest negative values of these electrode potentials to highest positive values. So this is the highest negative value and this is the highest positive value. So this is how the elements are arranged. Elements are arranged in an electrochemical series. So then the more negativity, no more negative sign or the more negative indicates the loss of electrons and get oxidized easily. It loses electrons and get oxidizes easily. So what are the applications? Why do we really have to consider these electrochemical series for any applications? Because it has the ability to calculate standard EMF of the cell. Then it will also give us an idea of how whether the oxidation or reduction takes place. Then the displacement of one element by other element. If we want some reaction to take place, we can check the electrochemical series whether this element can be replaced by the other element or not. Then spontaneity or the feasibility of redox reaction, whether the the reaction will take place or not, and hydrogen displacement behavior in the cell. So the first application is the calculation of standard EMF of the cell. So the EMF of the electromotive force of any cell can be calculated by taking the values of electrode potentials of two half cells. So this is one half cell for a galvanic cell, half cell. This is another half cell. So considering the potentials of any of these half cells, we can calculate the EMF of this whole cell. So there are some three methods. Oxidation potentials of anode can be used, reduction potentials of cathode, oxidation potential of anode, reduction potential of cathode, or considering the reduction potentials of both the electrodes, or considering reduction potentials of both the electrodes, or oxidation potentials of both the electrodes. So this is the strategies that can be used to calculate the EMF of a cell. For example, for a galvanic cell, so this is a galvanic cell, half cell electrode potential of half cell, that is a cathode. Cathode is on the left side in this picture. So for the cathode, and then minus potential of half cell of anode. Anode is on the right side here, zinc. So it has a half cell potential. So what is the potential of copper? Plus 0.34 minus 0.76 volts, that will give rise to 1.1 volt. This is the electrode potential of a cell. Okay. Then the other application is the relative ease of oxidation or reduction. So whether oxidation takes place or reduction takes place, we can decide from the arrangement of these electrochemical series, the electrodes in the electrochemical series. So metals are at the top of the series are good at giving away electrons. So the metals which are at the top of the series are good at giving the electrons, and the reducing ability increases as we go up the series. So the reducing ability increases as we go up the series. The metals at the bottom of the series are good at picking up the electrons and good oxidizing agents. So the oxidizing ability of the metal increases as we go down the series. Oxidizing ability increases as we go down the series. Increases. Okay. So, for example, lithium will give off electrons easily. So, the more the negative E naught value, the more position the equilibrium lies to the left. The equilibrium lies to the left. So, then the other application is the displacement reaction. So, for example, there are some reactions going on in our region, so we want to understand why is it going on. So for that, these displacement reactions are the best examples where displacement of metals are done. So any metal placed above in the electrochemical series so can displace metal below the series. For example, iron is placed above, this is above, this is below. So iron is above the series and copper is below the series. So it will displace the copper. It will displace the copper. For example, iron nail is dipped in a copper sulfate solution. Copper sulfate solution. So this copper is reduced to copper metal. Copper metal. Copper metal. So this metal gets deposited on zinc nail. Iron nail that is placed in copper sulfate solution. So this copper 2 plus ions in the copper sulfate solution take up electrons and forms copper. So this will get deposited on this nail. Then other application is the displacement of non-metals by other non-metals. So reactivity of non-metal increases from top to bottom. Reactivity of non-metals increases from top to bottom. This is a series from top to bottom. The reactivity increases. So non-metal placed below the series displaces the non-metal placed above the series. So the non-metal which is placed below, like chlorine displaces iodine from Ki solution. If we take a Ki solution and add chlorine will displace iodine. So chlorine is placed below the iodine. Chlorine is placed below the iodine. So iodine is above the series. So chlorine will displace the iodine in the Ki solution. This is other example for the non-metals. Then the applications also includes the spontaneity of a reaction. So how the spontaneity or the feasibility, whether the reaction will take place or not, can be determined from the electrochemical series. For example, copper and iron. Where if we, for example, iron is dipped in copper solution. This is iron rod dipped in copper sulfate solution. What happens? There is some reaction taking place. Some reaction takes place. So this copper get deposited on iron because of its this potential E cell potential, where it is positive, and the Gibbs free energy will be negative, and spontaneous reaction will takes place. Spontaneous reaction will takes place. So if, for example, if we dip a copper bar into iron sulfate solution, what happens? There is no reaction taking place. There is no deposition taking place. Why? Because the voltage, the E cell value is negative. And non-spontaneous reaction. It indicates non-spontaneous reaction. It means without any passage of current, there is no reaction. So That is one example where spontaneity can be understood or can be judged depending on the electrode potentials of the elements or the metals. Then determination of standard free energy and equilibrium of a reaction. So this is very important because this free energy also gives an idea of Gibbs free energy and spontaneity, and also equilibrium, where equilibrium state is reached in a reaction. So we know that delta G is equal to delta G naught plus RT log Q. Q is reaction coefficient. Q is reaction coefficient. So at equilibrium, delta G naught is 0. So at equilibrium, there is no reaction. So G naught is 0. So then what happens? Delta G is 0. G here that 0 is substituted. So it becomes 9 minus delta G naught is equal to RT ln K. It is again log is substituted is 2.303 RT log K. So on rearrangement, log K is equal to minus delta G by 2.303 RT. So we know that the minus delta G is equal to NFE naught. NFE naught. So log K here the minus delta G is replaced. This is replaced by this equation. So we get log K is equal to NFE naught by 2.303 RT. So this E naught is nothing but equilibrium constant. Equilibrium constant denoted as KEQU. Equilibrium constant for that particular reaction. So if for example we get some values for this after calculating. So if K is greater than 1, products are favored. So the delta G will be 0 or negative. If K is equal to less than 0, so negative. If K is equal to 1, then it is neither the reactants nor the products are favored. It will be at equilibrium. So delta G is 0. If K is less than 1, reactants are favored and delta G will be positive. So what is this equilibrium constant? We will see in detail. So for any reversible reaction, there is some reaction going on, A plus B is equal to C plus D. So it is reversible reaction. So there is a reaction going on from reactant to product, product to reactant. At some time after the reaction takes place for a long time, at some place there will be an equilibrium reaching. There is an equilibrium, it will be reaching. So that is nothing but equilibrium state. So the free energy will be 0. It is equilibrium. So this Kc or this KEQU equilibrium constant will give an idea or a relationship between the products and the reactants. When it is at equilibrium. So at particular temperature, rate constants are constant. So the ratio of activity or rate constant of a forward reaction to the rate constant of backward reaction should be a constant. Rate constant of forward reaction to rate constant of backward reaction should be constant, and that is called equilibrium constant, represented by KEQU. So it is given by a formula. KEQU is equal to forward equilibrium at forward by equilibrium by backward. So this is replaced by the activity of these reactants or products. So this is the product and reactant and its coefficients given. So it is nothing but products and the reactants in a ratio. So it indicates the equilibrium constant is measured in moles per liter. It is measured in moles per liter. What are the applications of equilibrium constant? So this equilibrium constant has very good applications, like it will help us understand the extent of reaction, like what is the reaction it is going on. So this will predict the extent of reaction or the degree of disappearance of reactants. When a reaction is taking place, it is going to form a product indicating the disappearance of reactants. So the magnitude of equilibrium constant gives an ideal amount of reactants and products. So this will indicate the amount of reactants and products. So if for example this is the reaction taking place, so these are the reactants, these are the products. Okay, so the for example, if we get a value like if the equilibrium constant is greater than 10 power 3, then it indicates forward reaction is taking place. Forward reaction is taking place. So here the formation of water has a value of equilibrium constant value of 10 power 47, 10 power 47, indicating it is greater than 10 power 3. So it favors forward reaction. Formation of water is favored. For example, if the equilibrium constant is has intermediate value like 10 power 3 minus 3 to 10 power 3, that it indicates the concentration of reactants and products are comparable. So they are almost equal, comparable. Okay. Then at lower equilibrium constant of 10 power minus 3, less than 10 power minus 3, like 10 power minus 48, then it indicates that backward reaction is favored. For example, the splitting of water, H2 gas and water, oxygen, it indicates backward reaction is favored. It is always favoring the formation of water. So these are some of the examples and the use of equilibrium constant. Then the other application is the predicting the direction of the reaction. So it is similar like the previous one, like it will indicate the direction whether it is going forward or the backward. So at equilibrium, Q is equal to K. Q is nothing but Q is reaction coefficient. Reaction coefficient. So is equal to K. K or is the equilibrium constant. Okay, if the Q is greater than K, if the Q is greater than Q, then it will shift the reactions to left. Shift the reactions to left. If the Q is less than K, if the Q is less than K, then it shifts to right. So as we see from these bar charts, we can easily understand that Q is less and K is more, indicating products formation. Q is more, K is less, indicating reactants. I mean, a backward reaction. So this is how we decide the direction of any reaction using equilibrium constant. So the other example is the application is the hydrogen displacement behavior of metals or any elements in the electrochemical series. So as we see this series, we can see that hydrogen displacement reaction takes place. Zinc and iron, for example, zinc and iron lie above the hydrogen reactive series. This is the hydrogen. So this is the hydrogen. There are some metals above and below the hydrogen. So below the hydrogen, below no reactivity or unreactive. Above reacts with acid and reacts with water. These all will react with water. These all will react with acid. So for example, zinc and iron lies above the hydrogen, lies above the hydrogen. So they can replace hydrogen and can replace hydrogen and can replace hydrogen in the reaction. So for example, zinc plus sulfuric acid gives rise to zinc sulfate and H2 gas, or iron sulfuric acid gives rise to iron sulfate and H2 gas. So gas is evolved. H2 gas is evolved. So this has good applications in preparation of H2 gas. And then copper lies below the hydrogen. So there's no reaction or cannot displace hydrogen from the acids. See, copper is below this under non-reactive or unreactive block. So it cannot replace the hydrogen from the acid. And also the above one, all the metals above can replace hydrogen, but a caution, there is a caution where sodium potassium react violently, like they are highly reactive with water, so they react very, very violently with acids, so they should never be used with acids, and that causes, because it causes explosion. So that some basic rules we have to understand, and also cautions us. This electrochemical series will help us in understanding this chemistry of the metals. So then Nernst equation. What is Nernst equation? This is the Nernst equation which is given E cell is equal to E naught cell minus RT by NF ln activity of products by activity of reactants. Why is it required? It helps in predicts the EMF of the cell. EMF of the cell when the conditions are not standard. When the conditions are not standard. So, for example, activity is effective concentrations of the metals or the elements present in the electrolyte. In dilute solutions, it is represented as molar concentration. So, for example, voltage difference between electrodes. For any electrochemical cell, two electrodes are present. So, voltage difference between electrodes is given as cell voltage or E cell. E cell. And at standard conditions, it is E naught cell. At standard conditions, E naught cell or E naught. So for spontaneous reaction, both E and E naught should be positive. Both E and E naught should be positive for a spontaneous reaction. So the derivation of Nernst equation, let us see. Like for example, this is a general equation where Mn plus takes up electrons and forms a metal. This N will be always 1 in the case of metals. So in a reversible reaction, electrical energy is produced at expense of decrease in free energy. So it is given as delta G free energy delta G is equal to minus NFE. So at standard conditions, G naught. Delta G naught is equal to minus NFE E naught. Okay. The decrease in free energy delta G associated with an equilibrium condition or the reaction is given by. So this is the equation for at free energy, decrease in free energy at equilibrium with the equilibrium reaction. So delta G is equal to delta G naught plus RT ln Q. So Q is the reaction coefficient. So substituting 1 and 2 in 3. 1 and 2 in 3. 1 and 2 substituting 1 and 2 in 3 gives minus NFE is equal to minus NFE naught plus RT ln Q. So on rearranging, this NF will be cancelled. So E is equal to E naught minus RT by NF ln Q. So the calculation of single electrode reduction potentials from the standard electrode reduction potentials for any atom can be done using Nernst equation. So from a single electrode potential and standard calculation of a single electrode potential can be done from standard. If we know the standard electrode potential, like from the electrochemical series, we can calculate the single electrode potential using this Nernst equation at non-standard conditions. So E reduction is equal to Mn plus, that is converted to Mn is equal to E naught by Mn plus converted to M minus 2.303 RT by NF log 1 by Mn plus. So this is products, this is reactant. So 1 is nothing but here the coefficient, like N is equal to 1. So there are some other applications wherein this is a summary of applications for the Nernst equation. So if we consider this equation, the concentration of one species can be calculated if the concentration of other species is known. So from the reaction coefficient or the activity from applying the activity of a reaction, the concentration of one species can be calculated if the concentration of other is known. It can be used to find the number of electrons involved in a redox reaction. Number of electrons can be calculated from a redox reaction. The pH of the solution can be obtained, which is nothing but negative logarithm of H plus ions. So the constant activity is replaced by H plus ion concentration and can be determined. So the pH that will give rise to pH. then it will help in finding the equilibrium constant of a reaction. So for finding the equilibrium constant, there is a relationship between the E cell and the K. K is nothing but the equilibrium constant. Equilibrium constant. So there is E naught cell is equal to RT by NF log K. So from this equation, rearranging the equation, we can find out the equilibrium constant of a reaction. So it will help in studying the effect of electrolyte concentration of a single electrode potential. Effect of electrolyte concentration of a single electrode potential. So the concentration can be varied and studied. Thank you. Thank you so much.
Like, share and subscribe. Hit the bell icon for more updates.